Good morning, everybody. So welcome to the second day of the SEFM conference. Today we will start with the keynote, and it's my real pleasure to introduce Mariëlle Stoelinga. And her work is basically in the area of safety and formal methods. She has formalized semantics for dynamic fault trees with interactive Markov chains. This was really cool work. And today she will talk about maintenance and how safety and faults become together. So it's a pleasure to hear you.
Thanks, Max, for the introduction. Yeah, I'm very excited to be here and talk about a topic that is, that I find really interesting and that recently gained my attention, namely predictive maintenance. The title in the preceding set. Predictive maintenance means model checking, but I hope to convince you that this is a real exciting research topic where we as software engineers and as formal methods people, we have a lot of techniques to offer and a lot of really exciting research questions to answer. I'll do two things. I'll give a more high-level overview of what is predictive maintenance and also go into some of the details of things that we can do with stochastic model checking. So maintenance, predictive maintenance is a very innovative maintenance concept where you try to predict failures better, and then you can devise relevant maintenance actions to prevent such failures from happening. And predictive maintenance is a really buzzword. It promises you higher reliability, higher availability, streamlined service calls, lower costs, reduced downtime. And of course, that sounds very good. This is what everybody wants. But let's contrast predictive maintenance to more regular maintenance types. And there are a couple of types. You have corrective maintenance. That is what it's also called run to failure. And that is what you do, for instance, with your light bulbs at home. You just wait until your light bulbs fail and then you just replace it. And then, of course, the question is how many spare parts do you need in stock in order to replace broken light bulbs? Then there is planned maintenance. And this is what you do, for instance, with the filters in your car. Your maintenance handbook of your car states after 25,000 kilometers, replace your filters. Then this is planned, and the question is then decide on the maintenance intervals. How many kilometers, how many hours can your filters stand before they degrade and they need to be replaced? So that's planned maintenance. So with fixed maintenance intervals. Then there is condition-based maintenance. An example here is the tires of your car or of your bike. Because what you do is you check the profile, and if the profile is still big enough, then you keep on riding. But if the profile is too small, then you replace it. And the question is then to decide on inspections intervals. How often do you need to inspect your tires in order to, catch failures on time? But today we're talking about predictive maintenance, and that's much more about continuously monitoring failures, predicting when things fail, and then devise the maintenance actions based on your failure predictions. And here, of course, monitoring with sensors is the big thing to do. So far so good. So predictive maintenance, it promises better performance, because if you do planned maintenance, you do maintenance much too early, meaning you spend a lot of money on maintenance, and that's too expensive. But if you do maintenance too late, corrective maintenance, then you will experience lots of failures, which are even more expensive than maintenance. So predictive maintenance is all about just-in-time maintenance, doing maintenance exactly when and where it's needed, and that it balances costs. So here, there's an example. Here you have a gearbox, and Well, after when it's operating, you will experience all kinds of things. When it here the conditions start to change, when the gearbox degrades, you will hear things. You will hear ultrasound. Then you will observe vibration, more power usage. You will hear noise. The thing starts to warm up. Then if it's worse, smoke starts to emit. And in fact, you can all detect that. And if you keep the gearbox in a good condition, then you will be able to prevent this all from happening, and you will prevent expensive failures. So what you do is often via sensors, you do anomaly detection. And if you experience funny phenomena that are out of the ordinary, so outliers, then it's time to take action. But the question, of course, there's a lot of exciting research questions here. So the question is, of course, which sensors do you need? How do you want to monitor acoustics or vibration or temperature? What's a good thing to measure here? Also, how many sensors do you need? Where do you need to place sensors? Which algorithms do you want to use for anomaly detection and on all kinds of neural networks? Then another whole nice area is decision making under uncertainty. So those predictions are never perfect, so they come with uncertainty, and how to turn these predictions into a good maintenance policy. Which actions do you want to carry out? When do you need them? Where do you need them? And of course, also clustering them. You don't want to, let's say, open the work on the roads 1 week to resolve this issue, and the next week to resolve another issue. You want to cluster maintenance as much as possible. And of course, there are lots of optimization techniques come into play. So this is the predictive maintenance workflow. What you do, you start, of course, with data acquisition. Based on the data, you prognose how you predict your failures with prognostic algorithms. Then you turn those prognostics into a planning and a logistic plan. You implement that, and well, then fun starts all over. Because on your new maintenance plan, you will again acquire new data. This is, of course, this workflow is not special for predictive maintenance. It's a general workflow, what you do for predictive analytics. If you want to sell more books on Amazon, then you also acquire data, prognose sales, do planning and logistics. If you want to sell more books, and so on. So predictive maintenance, does it work? Well, there have been a few reports by consulting companies like McKinsey, and McKinsey claims that predictive maintenance is the most promising application in the Internet of Things. They predict 36 billion of cost savings a year, and they say that 50% downtime reductions are possible if companies implement this scheme. However, there's another report by Price Waterhouse that says, okay, it can be realized, all those benefits, but it's not easy. And there are a few bottlenecks, especially on the scalability, robustness, and accuracy of the prediction algorithms, of the prognostic algorithms. Also, solutions are not leveraged, meaning everybody is still working in their own silo. Sensor people know everything about sensors, but don't talk to the optimization people. And automation of the workflow is another big issue, because a lot of things are done manually in the predictive maintenance workflow. So then what is, in my opinion, in for software engineering? Well, here, or on the sensor side, we can still work a lot on the semantics of sensors. What do they really mean? How do those sensors combine into meaningful information? For the prognostics, there's a lot of exciting work on, of course, data analytics, but also combining data with models, as I will tell later today. Then for optimization and planning, so planning and logistics, of course, all the fun optimization algorithms we have can be deployed here. And for implementation, what is very important is stakeholder alignment. That's maybe something a bit more on the social sciences. Yeah, it's very important that stakeholders have the same vision on predictive maintenance. Because if some maintenance solution well, it's not shared, so let's say one party pays for the maintenance and another party reaps the benefit, it's never going to work. You see this a lot, for instance, on in railroads, where the asset owner, like Deutsche Bahn, they own the rail and they have profit from pure failures, but the maintenance is not done by Deutsche Bahn, it's done by subcontractors. If they make all the costs for predictive maintenance, don't get the benefit, this is never going to work. Anyways, and I think throughout, so better coordination throughout the workflow with techniques like model-based software engineering, domain-specific languages, protocols, and so on and so on. This can really improve the situation here. Because a lot of programming is done by engineers, and we as computer scientists can do better. Anyways, so one of the things I'm working on is on a large project. It's called Primavera, and our goal is to make predictive predictive maintenance easier and also more effective by having a more holistic view of this whole cycle. And hopefully we can help realizing the true potential, higher reliability and availability at lower cost. Anyway, let's now look at some of the specifics, and especially concerning prognostics. So prognostics, it's defined as predicting the time at which a system or component will no longer perform its intended function. And there's a few metrics for that, like performance indicators, so such as the remaining useful lifetime, availability or the average uptime, the reliability, the probability that the system fails before its mission time T, the expected cost of failures plus maintenance. Those are all meaningful ways to measure those prognostics. There are two main approaches towards prognostics. We have model-driven prognostic algorithms and data. And model-driven models, well, there are several variants here. Those can be physical at component level. You can have ODEs, finite element models like this one, differential equations like here, but also fault trees, as I'll tell you later. And they were mainly developed from the 50s and the 60s. Then we have the data-driven models, and here you have all your favorite data analytics stuff with neural networks of various types, Bayesian networks, and support vector machines, decision trees, and so on. And of course, I mean, you know this, but when I tell this to engineers, they're a little bit surprised that those are also developed in the 50s. Of course, both approaches have their pros and cons. Here, the model-driven approaches, of course, you need to construct your model, which require a lot of expertise. But in particular, you can only make such a model if you know the exact operational condition. You need to know the material, you need to know the stress, you need to know the temperature, the load, etc. And then those models can predict, for instance, how much wear is incurred. So those models can tell you exactly how much material is removed from a rail or from those tools when you use it. And of course, the nice thing is that they are white box, they are very much explainable, and they focus on failure mechanisms. They really focus on why does the system fail. This is, of course, very much unlike the data-driven approaches where you use, where you put in lots of sensor information, and this neural network spits out whether or not you have an anomaly or when you can expect your next failure. This is fast. You don't need to know the exact failure mode, but the problem is that you need a lot of high quality data, and this is actually hardly available at the moment. I've worked with various companies, and they say they have a lot of data, and but when you look what that data is really about, it's not good enough to really predict failures. And of course, as we all know, the data-driven methods, they're not explainable, they're black box methods. They don't tell you why systems fail or degrade, and they are focused, of course, on correlations, but not on causations. That is why, a key challenge is to combine both, and to reconcile domain experts with a failure mode analysis and data analysts with a correlation. And actually, this whole synergy between model-driven and data-driven approaches is again not unique for predictive maintenance. It's pervasive in predictive analytics altogether. It doesn't matter if you predict sales or you predict human behavior. All the time, what pops up is, well, maybe you have sales models or psychological models, you have data, and combining those is one of the, I would say, pervasive challenges in predictive analytics. Of course, people have already worked on this. There's hybrid prognostics where the two are combined. And there are three main approaches. You can do model to data. You can use models to help the data analytics. For instance, via accelerated learning, where you pre-configure your data-driven meta via data via models. And what is often done is data augmentation. If you don't have enough data here, which is often the case, you use a model to generate synthetic data. The question is, of course, how good is that synthetic data? And also for data validation and data cleaning, you can use your model to see if your data makes sense, if there's no errors, and so on. And data cleaning is a very hot topic because data scientists tell me that 80% of the time is going to the cleaning and only 20% of the time is going into the analytics. And I think here, I mean, in all three topics, there's lots of things that that are still to be done and where we as software engineers can help. Then there's data to model, where data helps model-driven approaches. Of course, very classic is to fit model parameters. Can you figure out the exact load, the exact operational conditions? A dynamic variant of model parameters of fitting is parameter trending. So can you not only figure out the current values of your parameters, but can you also predict the future values of the input parameters to your models? And then you can use those parameters trends to predict the future behavior of your system from your parameter. A topic that has gained recent attention is called so-called model learning. Can you infer the whole model from data? For instance, can you learn a finite state model that models your protocol? I myself work on inferring fault trees from data. Then there is things that work in parallel. There is a lot of work done in so-called physics-informed neural networks, where you really use those laws of physics to infer your neural network. I'm not an expert at all on this. And there's, of course, also reinforcement learning, also a hot topic that I feel is also using models and data at the same time. And this reinforcement learning has already also been applied, of course, to predictive maintenance, and the results, they are very promising. At least the papers I read, they show convincingly that reinforcement learning does outperform classical optimization for maintenance optimization. So now let's move into one of my favorite topics, which is fault tree analysis. So what are fault trees? Fault trees, those are graphical models that tells you how systems fail. So they tell you how component failures propagate through the system and then lead to system failure. There's two types of analysis that you can do with fault trees. There's qualitative analysis that pinpoints you to root causes and critical parts, and there's quantitative analysis that where you analyze metrics or key performance indicators, such as the reliability, the probability that no failure occurs during your mission time, and the availability, the average percentage of time that your system is up. And there's lots of commercial software tools that do this for you. So, and fault trees, they are a model that are used a lot of industry, a lot in industry, and they are not only used by industry, they were actually invented by industry. So sometimes I talk to reliability engineers, and they say, "Oh, all those scientists with the difficult models. Why do we need those?" But well, it's industry who came up with such models. Okay, then if you want to know more, then you can read this beautiful paper here. But let's go to an example, and this is one of my favorite examples, where you go on a road trip, and as a preventive measure, you take your phone. So your road trip fails if both your phone fails and your car fails, which is indicated by this AND gate here. Well, your phone can fail for several reasons. I listed two here. So either your connection can fail, or you can be out of power. So this is an OR gate. And well, your power, it's again an AND gate, because for your power to fill either your battery, the battery of your phone could be empty. However, if your engine is still working, you can use the engine of your car to power up your phone. Then your car can also fail for many reasons. I've listed two here. Either your engine can fail or your tires can fail. But for tires, well, especially older cars, they still have a spare tire. So your tires only fail if 2 out of your 5 tires fail. So if the first tire fails, you put up your spare and then still run. As I said, you have two things can be done: qualitative analysis, identify root causes and critical parts, and quantitative analysis focus on metrics, in particular reliability and availability. And what they do is they assume probability distributions over the components, over the leaves. So for instance, those can be the parameters of an exponential distribution. And then what people do is they compute the failure distributions for the road trip. So if this all fails with an exponential distribution, the question is, what is the distribution for the road trip to fail? And but now if you look, for the road failure, so you look at the top level event. But now, okay, let's now look at dynamic fault trees, because those fault trees here are static in the sense of they have only Boolean gates and no dynamic behavior. But people start to realize that actually you need more dynamics, in the sense that if you look, when does your road trip really fail? It's not an AND gate per se, because your road trip only fails if first your phone fails and then your car fails. Because if your car has failed, but if it fails in the other way, if your car fails and then your phone fails, it doesn't matter, because you have already used your phone to call a road service. So it's only in this order. So this is modeled by a PAND gate, a priority AND gate, where subsystems have to fill in the right, from left to right, the right order. And the same holds for your tires, because what's the idea here, that if your tires can be either active or passive. So active is when they are in use by the car, but they're passive and sitting on the trunk, they don't fill as often. So they have a reduced failure rate. And this is modeled by those spare gates over here. It's a little bit more complex, but the idea is that, well, active tires have a high failure rate, and when you and passive tires have a lower failure rate. And then still the question is how to compute the failure distribution. So so there were these dynamic fault trees, but all people started claiming that, oh, this was too difficult. Quantitative analysis is troublesome. They require a lot of manual effort. And my claim is that we, meaning you, meaning for the formal method community, we have developed so many tricks to crack large fault trees that this is a nonsense. And especially what we've done is applies to stochastic model checking. For instance, also Alessandro, he worked on this topic. And so what we do, we take our dynamic fault tree, generate the state space, and then do stochastic model checking. And we have done a lot of smart tricks to make this really work. For instance, smart state space generation with using compositionality. Maybe you detect that some states do not matter. You can do a partial state space exploration where you can either optimize, be optimistic and pessimistic. We have a gazillion of reductions techniques to make state spaces smaller, like partial order reduction, bisimulation reduction, symmetry reduction, and whatnot. Then we have smart algorithms, stochastic model checking, method-specific computations. If it doesn't work, you can do simulation, Monte Carlo simulation, and fitting it all together with some meta modeling. Okay, and this is also a nice technique, graph rewriting. Maybe what we've done here is to rewrite the fault tree before you generate any states. So if you manage to massage this fault tree such that it spits out your states, that can help a lot. For instance, you can imagine if you have two AND gates on top of each other, you can combine those and have pure states. Anyways, what we've done in particular, this is what Lars told in the introduction, to have a compositional semantics in terms of interactive Markov automata. So rather than building from your fault tree one large, gigantic Markov model, a big stochastic model, we do this in a compositional fashion. So each fault tree element, each gate, and each leaf get their own Markov model, and then we compose it all together. And this helps especially if you want to be more flexible, because in this way you can be it's more flexible. If someone comes up with a new gate, you only have to come up with a Markov model for that gate, and then everything works again. Or if you want to change the semantics of the gates, again, you only change the Markov models to assign to those leaves, but the Markov models for the gates remain the same. And of course, we also do a kind of smart composition where we compose those small models one by one, and each time after each composition, we reduce to get rid of more states. Let's see what. And in this way, you can accommodate degradation behavior quite easily. What you can do is, for instance, this subsystem fails if more than two tires fail. So what you do is, rather than saying, okay, either a tire is operational or it fails, you can use degradation levels. So here your system is perfect. Here it has failed, but in between you have some degradation levels. For instance, rather than making this one step with parameter lambda, you can make it an Erlang distribution where you move where each step has is governed by an exponential rate of lambda over 4. And then you can introduce repair actions, because if you discover that your system is not so in a great state, you repair your system and you move to a better state. And of course, this already triggers a nice optimization problem, because repairs, of course, they cost money. When do you need to repair your system? I suppose I want the cheapest policy that still allows me a reliability of 99%. What is a good policy here? And you can also explore different options here, different repair policies. If multiple components fail, do you repair them on a first come, first served basis, or do you assign priority, and so on? And we use this to analyze a railroad component, namely the electrically insulated joint. And this is actually it's this device over here, and it electrically separates the tracks. And there are quite a bit of joints in the Netherlands, and they are an important cause for train disruption. So if your train doesn't go on, and then they say, it's announced that there is a signal failure, it's often this guy is often the culprit, is often to blame, because this is a fail-safe system, meaning that if any problem is discovered, the system returns to a safe mode, and all signals are set to red, because then no trains can collide. So whenever a problem is discovered, whenever a problem is discovered here, things are set to red. And the purpose is, as I said, to electrically separate tracks, meaning that so that trains can be detected here, whether they are on this section or whether they are on that section. So this is the fault tree that we made out of that, and we investigated several maintenance regimes where you don't know inspections at all, and then you say very high unreliability. If you do 1 inspections per year, 4 inspections per year, 8 inspections per year, and of course, after doing an inspection, you also take appropriate action, right? And here you see the maintenance costs. So you see, and here you see that if you do no maintenance, you have a very high cost. But so if you have do no inspections, your costs are very high. If you do, so here it's no maintenance, costs are very high. If you do 1 inspection per year, it decreases, and well, after a while, it doesn't matter anymore to do more inspections. And so the people at ProRail, for whom we did this case study, they were quite happy with this analysis, because later they wanted to pursue a new joint, and then they used this model to compare the performance of the new joint compared to this joint over here. So one problem that may occur is, so this we didn't do with model technique simulation for this, but one problem that you may encounter is if you do simulations, is that failures are very rare, and if you have rare events, you need a lot of samples to observe the phenomena of interest. And what we worked on is so-called rare event simulation techniques. What you do here is that you first increase the probability of a rare event and compensate for this increased probability later. And this leads you you need fewer samples in this way, and this yields faster and more accurate simulation results. And one small example is this. I suppose you have a coin, and the probability on heads is only 1%, and the probability on tails is 99%, and you're interested in estimating this probability of in seeing how often you reach the red state. So what you can do is you can increase the probability of the rare event to 10%. Then you need much fewer samples, but rather than counting each hit of the red state as 1, you only count each red state as 1/10. And this way, the expected number of occurrences of red in your simulation run is exactly the same. Still, your variance is a lot lower, so you need much fewer samples. And you can also do this for exponential distributions. If this is your failed state, you increase your probabilities, your failure probabilities, and you decrease your repair rates. And in this way, you have much faster simulation. And the nice thing is that for general rare event simulation techniques, this is often done manually. An expert needs to know, okay, those are the failure distributions, so we need to increase those, and those are the repair distributions. We need to decrease those. But the nice thing is for fault trees, they're so nicely structured, this can be done automatically. And here is, here you see that things are both, the simulation time is much lower. So here's another railroad case study. And especially for this rare event simulation, which is the green bar, it's constant. If you blow up your model, for small models, still normal Monte Carlo is faster, but when your model start decreases, this start blowing up, and the same for the other case study, the fault tolerant processor. And you also see that this is Monte Carlo simulation, this is rare event simulation, and this is statistical model checking. And here we always got results. Here we got here we had memory timeouts, and here we needed too large. So our samples didn't get meaningful accuracy. Those are the this is the confidence intervals, and you see that for rare event simulation, confidence intervals are much narrower than for regular Monte Carlo simulation. And for, of course, if you do exact model checking, you get exact results. So this is a nice, faster and more accurate results automatically if you use these techniques from rare events. Yes, well, then finally, some work that I have been working on recently. I think it's a bit related to things you do, Bas. It's an uncertain parametric fault. Because the problem is, of course, that the failure distributions for the components, they're often unknown. And what we've worked on is on a kind of Bayesian approach, where we assume that each of the lambdas, so each of the failure distribution is governed by is taken from an unknown distribution, and it even needs not to be exponential. And then we can, of course, with Monte Carlo-like techniques, estimate probability for your fault fail. And that is what we do is we use a technique called scenario optimization. So you first your sample or your parameters, then you instantiate your fault tree or your market gain with those parameters, and you compute failure probabilities. And you do this a number of times, and then you from your samples you compute your actual value. And the nice thing is that with this novel technique called scenario optimization, you can get much better guarantees. So traditional Monte Carlo simulation yields confidence intervals, but with this scenario optimization technique, you get so-called PAC bounds. This stands for probably approximately correct. So you can say with probability 2%, the computed results deviate no more than 5% from the actual result. This is how it works. So what you normally do is you have your fault tree, For instance, this parameter equals 2, that parameter equals 5, and then you obtain probability. But with uncertain parametric fault trees, what you do is that you assume those rates themselves are governed by probability. Well, if you instantiate this, for each sample, you get your own reliability curve. But now with scenario optimization, you can actually bound this. You say, okay, with I see lots of curves. No, I see most of the curves are in this red area here. So I know that, let's say, with a probability 5, with probability 95%, my curves, my reliability fall in this curve. Well, I make the picture very large, but hopefully it's in real life a bit narrower. And here, this is a more narrow bound. Let's say this is probability 90% to actually in this blue, much narrower area. So you can really bound the probability. And yeah, this is not so easy because this scenario optimization techniques, what they do is they balance precision versus tightness. So this very tight bound, you have to decide. So in this tight bound, you have to see where is this tight bound. I want, let's say, probability 90% here. Where should I move this bound? I should have here or there or there. And this is done by setting up a linear programming problem. And also, what we also worked on is on batch verification, because you can see that you do a lot of sampling and all the time you're solving the same problem multiple times, and we want to speed that up. To reuse results from previous computations. Anyways, let me just mention that we also work on methods for learning fault trees from data. So normally you have a fault tree, you compute risk, reliability. Here we have data and we construct the fault tree from data, and we do this especially with genetic algorithms. Anyways, then if you're interested in fault trees, we have a benchmark suite where you can well, reuse our fault tree models. If you have fault tree models for us, we're very much interested in having them in our beautiful forest of fault trees. And yeah, this is the overview again of what we do. That's model checking, but this is, I want to conclude with this slide because I really feel that in the whole field of AI, a lot of work is done on data analytics. I feel software engineering, what we are all working on, is actually the most. And that concludes my talk.
So it's time for questions. I would start with the first question and then go to the back. With the learning of the fault trees, most fault trees, they have some rare events. So how certain are you that your fault trees are correct, which you have learned from?
Yeah, this is of course not an easy question. It's a downside. What you need is good representative data, and actually you need to see all failure combinations at least once. So that is not so good. On the other hand, I believe that the main application is not learning a whole fault tree, but rather learning a fault tree with holes. Or suppose you have a fault tree, but things have changed, but your model was not up to date. So what are then the where do you need to repair things, or what if you have certain parts where you're uncertain about? Then you can, I feel you can use those techniques to fill in the gaps.
Okay.
Yeah.
Well, thank you for your talk. I liked it very much. You presented a lot of, let's say, modeling formalisms and then analysis. Where would you say is the main computational challenge in the analysis of these models?
Yeah, that's a good question. So of course, the problem is mainly in this dynamic behavior. So if you have, let's say, static behaviors, ands and ors, and then you can use PDDs very efficiently. Your fault trees are Boolean; they are in fact a Boolean function. So PDDs, but once you have those dynamics, you need to be smarter. And of course, we have worked on combining PDDs for the static parts and model checking for the dynamic parts, but there the story has not ended yet. And maybe for industry, what industry finds difficult is coming up with the model themselves.
Can you give us a high-level idea on how you learn this fault trees? How does it work?
Yeah, this is basically what you often do with genetic algorithms. So you start with an initial population, and then you start mutating that initial population. So what you can do is you can replace AND gates by OR gates. You can switch branches. You can move subtrees up and so on. So I think we have like 18 rules, 18 mutations for that.
Thank you for a nice talk. I have a follow-up question to the genetic programming part. So I also worked with genetic programming once, and the thing with meta-heuristic search is that you have a lot of parameters that you have to fine-tune. Do you also observe that problem, and what was your solution for that?
Yeah, this was a problem, and what's also a problem if you run it, since your algorithm is random, each time you run it, you have a different different solution. What we did look into a little bit, but we haven't fully explored, is that see which rules are better at the beginning and which rules are better towards the end. And if you're there, tuning that is can be very helpful.
I would have a question regarding to the beginning part of your talk, the proactive maintenance. And you said you can have multiple sensors which give you an indication about if the system may be failing in the future. So acoustics and so on. And let me tell you a story. So I worked on the past on a monitoring algorithm, stochastic monitoring. It's provable, optimal, that it gives you the right information at the right point in time. And then I got an information from a Japanese car manufacturer who said, yes, we used your algorithm to monitor exhaust emissions and see if an engine problem is occurring. And they said, we have improved your algorithm. Okay, this was something interesting. And the problem is basically they used multiple sensors and combined them, but all the sensors, they are interconnected, they are related to each other. So how do you know that your sensors telling you the same thing and giving you the same indication when the system may fail? So there could be a sound coming from the engine, there could be something in the exhaust and so on, but it's all the same problem.
So you mean the failure mode is the same, or
the sensor data you get, they are interconnected.
Yeah, so first of all, I'm not a sensor specialist, but what people do there is, of course, if they have multiple sensors all measuring the same, so they have those acoustic sensors that determine vibrations, then they check, then they kind of cross-check them with each other. If one sensor, because of course it could also be a sensor problem, and usually if there's let's say a crack in, for instance, concrete, the vibration pattern is completely different. So in that sense, there must be something weird, and and there are a lot of sensors fusion techniques that combine different sources, and so also cross-check with our other information, maybe for failure data and so on. But I'm not sure if I can fully answer your question.
I have not solved the problem. So for me, it's a problem to basically decorrelate dependent information sources. This is the main problem. To identify that some sources are correlated, and if you have in data science, you basically omit the data source which is correlated to another source. But in our case, these are rare events, and then these rare events pop up all at the same time. And this is what I don't know.
But what I can say is that what I see a lot, a company has data and they say, here we have data, please do your magic. And then of course that's not how it works. If you want to build a house, you cannot say, here you have some stones, please build a house. So you have to start from the goal, saying, what do you want to measure? What do you want to improve? Do you want to improve reliability or cost or what? And from your goal, you start designing your information architecture, your data sources, and then you do your predictions, and not the other way around. Hard to convince companies that it should be done in this way.
Okay, one last question.
Okay, thank you for the nice talk. I walked in late, but I was on the Zoom, so I enjoyed it. So I know you focus kind of on the fault trees, but kind of coming back to this data point, do you see industry being interested in some of the other methods for learning things? I know it was on an early slide, like using neural networks and these type of things, or what do you sort of see what the most interest is from engaging with industry in this space so far?
Well, I think industry, they are interested, and yeah, on the other hand, they really want to improve reliability and introduce or use or improve fault trees and find ways to model things better, to incorporate maintenance in fault trees, because current fault tree analysis can handle a little bit of maintenance, only limited, and by improving maintenance, that is what they like. They of course also like predictive, whole concept of predictive maintenance. They're very enthusiastic. Of course, it also requires investment and time and resources. Yeah, question is also where to start. Not sure if this answers your question, did you?
So let's thank Mariëlle again for this really nice keynote. It was amazing.